All right, let's jump right into this explainer. Today, we're building the ultimate toolkit so you can absolutely crush grade 11 physical sciences. We are focusing on a topic that is literally the bedrock of your entire mechanics curriculum, 2D vectors. Now, if you've ever felt completely overwhelmed by forces pulling in a million different directions all at once, you are in the exact right place. We're going to visually break this down step by step, using the exact guidelines straight from your CAPS documents.
We've got a really clear roadmap for today. We'll start with the foundation and definitions, move on to the Cartesian canvas, build up our component toolkit, tackle a boss battle past paper, and wrap it all up with closed vector diagrams.
Okay, part 1. The foundation, definitions.
So what's the big deal here? Well, as your CAPS document strictly outlines, it all boils down to direction. A scalar is just an amount, a magnitude, but a vector brings direction into the mix. Think of it kind of like this. Telling someone you drove 50 kilometers is a scalar. Telling them you drove 50 kilometers straight north, bam, now you're talking in vectors. That directional piece is going to be the absolute star of our show today.
And that brings us right to the core of our toolkit, the resultant. This is simply the single vector that has the exact same effect as two or more vectors combined. Picture this. You and a friend are dragging a heavy box from two different angles. The resultant is basically that single imaginary rope that would pull the box in the exact same direction with the exact same final force all on its own. It's like finding the ultimate shortcut.
Moving right along to part 2. The Cartesian canvas, visualizing vectors. Now, when you step up from grade 10 to 11, the game changes a bit because we drop these vectors onto a 2D Cartesian plane. We can actually map these forces right onto the x and y axes. Notice how we represent them with arrows? The length of that arrow is your magnitude, how strong the pull is. The arrowhead tells you exactly where it's going. And here's a pro tip for grade 11. We absolutely love it when these arrows start right at the origin, the 0, 0 mark. Trust me, it makes the math so much smoother.
Part 3. The component toolkit, breaking vectors down.
So what happens when vectors are acting at weird, awkward angles? Well, we just mathematically break them apart into pieces. By using some trusty trigonometric formulas, specifically, the horizontal x component equals r times the cosine of theta, and the vertical y component equals r times the sine of theta, we can figure out exactly how much a vector is pulling left to right and up and down. But, and this is absolutely crucial, you have to make sure that theta is the angle between your vector and the x-axis. Get that right, and these formulas work flawlessly every single time.
Let's take those formulas and build a master plan. If you follow this simple, methodical 4-step recipe, finding the final resultant becomes a total breeze. First up, always sketch it out. Second, break every single vector into those x and y pieces we just talked about. Third, sum up all your x's together and then all your y's together. And finally, step 4, bring in good old Pythagoras' theorem to calculate the magnitude of your total resultant. Easy, right?
All right, part 4, the boss battle, tackling the exam paper.
Here we go, the boss level scenario. This is an actual grade 11 paper 1 exam question from November 2025. Picture a 25-kilogram crate being yanked around by 3 different forces, all at different angles, and the exam asks us to find the resultant. We've got F1 at 700 newtons pulling up and to the right, F2 is 800 newtons pulling down and right, and F3 is 650 newtons pulling perfectly flat to the left.
Let's put step 2 of our master plan into action and break these down, starting with just the horizontal x components. Check out how the memo calculates this. It's all about that angle to the x-axis. For F1, the diagram actually showed it at 30 degrees to the y-axis. But remember our golden rule, we need the angle to the x-axis. Since a right angle is 90 degrees, 90 minus 30 gives us 60 degrees. So we punch in 700 times the cosine is 60, and boom, 350 newtons to the right. We do the exact same trick for F2, giving us 612.84 newtons to the right. And F3? Super easy. It's already lying completely flat on the x-axis, so it's just a straight 650 newtons to the left.
Now we tally it all up by summing the rightward components, that's the 350 plus the 612.84, and then subtracting that 650 pulling to the left, we get our net x component. It works out to exactly 312.84 newtons pulling right. Now in a full exam, you'd do the same for the y components and finish with Pythagoras, but establishing this net horizontal force is exactly what we need for the next really mind-bending part of this question.
Which brings us to part 5, closed vector diagrams, the final application.
So what on earth is a closed vector diagram? Well, if you draw all your acting forces tail to head, one after the other, kind of like tracing out a treasure map, and you end up exactly back at the origin where you started, you've made a closed shape, a polygon. But the really absolute key here is the second half of that definition. It means your resultant has a magnitude of 0. All the forces are perfectly 100% canceling each other out.
Now, the exam throws a really clever curveball. It asks you to explain why those three forces acting on our crate from the previous slide will not form a closed vector diagram. It's challenging you to connect the theoretical definition we just read to the actual math you just did.
And the answer is right there in our calculation, because we literally just proved that there's a leftover net horizontal force of 312.84 newtons. The overall resultant absolutely isn't 0. And if there's a resultant force hanging around, those arrows are never going to connect back to the start. The polygon simply cannot close, which means in the real world, that crate is going to accelerate.
And that leaves us with one final provocative thought for this explainer. Imagine you had to step into this scenario and perfectly freeze that crate in place. If you had to add a fourth force to make that vector diagram close flawlessly, what exactly would its magnitude and direction need to be? Think about how you'd mathematically wipe out the total resultant we were calculating to hit an absolute 0. Figure that out, and you, my friend, have truly mastered the 2D vector toolkit. Good luck!